All right, here we go. It is still Monday, October the 16th. This is part 2, 2023. It doesn't matter, okay? We'll just see. Principal quantum number. What does principal mean when it's spelled like this in this context? First or main. All right, this tells us the energy level of the electron. Okay, in Schrodinger's equation, it had to again be a whole number. 1, 2, 3, 4, 5, just like Bohr's model. So n is going to equal 1 through 7. It's going to be a whole number. So the electron again, is it working over there, John?
Yeah.
Okay. So the electron has to be in one of these distances. This is Schrodinger's wave equation. That's where the quantum numbers come from Schrodinger's very complex wave equations that I don't have enough math background to be able to understand fully. But these are just variables that limit how much energy the electron can have, because it can only have these fixed energies.
So each of those lines is an orbital?
Each of these lines is an energy level.
Okay.
Okay? Each of these lines represents an energy level. Hydrogen, this is a very simplistic model. We're going to complicate it a little bit now. Okay? But we're still going to use the same basic model. The second quantum number, though, now says it is equal to L, which is known as the azimuthal quantum number. Now, I never knew. I thought that was just some guy's name. And then when I moved here from Louisiana, 2001, the school had just opened. I'm living out in Chelsea. You done? Okay, you can go. I'm living out in Chelsea. They don't have cable yet out in Chelsea. At that time, they do now. Okay, but Chelsea was very small at the time. Houses were cheap. That's why I lived there. And we had a satellite. And my satellite wasn't working very well, so I was going through all the settings, and I all of a sudden saw this azimuthal coordinate system, azimuthal settings on the satellite. I said, I've heard that before. I didn't think it had anything to do with satellites. I thought it had to do with atoms and quantum numbers. So I literally pulled out we didn't have internet really fully yet. We were at dial-up at that point. If you've ever heard dial-up, it was super slow. I pulled out my 1963 set of World Book encyclopedias that had been in my family all that time. And I looked up azimuthal. And it turns out that it's a coordinate system, a geometric three-dimensional coordinate system that gives a location like of a satellite in space with an X, Y, and Z coordinate. That's what this azimuthal quantum number is doing. It's kind of giving a location in space where the electron is going to be around the nucleus in a three-dimensional coordinate system. Way more complex than just simple, but yet that's where it comes from. It's just kind of giving us an idea where the electron is going to be. Now, where the electron is going to be is dependent upon its energy. So we end up having L can equal from 0 up to n minus 1. Again, we have to limit the energy because the electron can only have fixed energy. So on the first energy level, when n equals 1, L can only equal, good math, Steve, 0. Now the actual value is not all that important. Just we only have one value. When you plug in to Schrodinger's equation, n equals 1 and L equals 0, it gives you an answer where the electron's going to be in a certain wave pattern, a certain way. And they get an answer. The answer is called a wave function. And the wave function to us is meaningless. And I don't know the math. Again, I'm just trusting that all these smart people were right. But when you square the wave function, it gives you a probability of where that electron is going to be in space given this amount of energy. When you do that, this is going to be called an s orbital. And s orbitals are all spherically shaped. So the hydrogen, if the electron's on a 1s in a 1s orbital, when you say 1s2, 2s2, 2p6, that means the nucleus is on the inside of this sphere, very tiny little dot. on the inside, and the electron's in some kind of 3D pattern going around the nucleus. But the Heisenberg uncertainty principle says we don't know exactly where or how it's going around. We just know that we have a 90% probability of finding the electron in this area given n equals 1 and L equals 0. Okay? Now, I've got more to that, but let's go to if n equals 2. L can equal 0 and 1. 0 up to n minus 1, but it's always going to be an integer. Okay? L equals 0 always means, and L equals 0 is an S. But L equals 1, anybody remember? It's going to be a P. Now, a p orbital is going to have a different shape. A p orbital is going to be more of a dumbbell shape. Again, it's a probability of where they find those electrons. Where are they going to be? Let me show you this. How to make super complex math. I'm trying to make it simple. Simpler. Come on, where is it? Here we go. So when we plug in, this is a 2p orbital. When you plug in n equals 2, L equals 1, and then we're going to find out there's a third m sub L, okay? When you plug it in, each dot represents where the electron might be. It doesn't mean that this hydrogen has all of these different electrons. These are just different locations on where the electron might be. So scientists, we just say, okay, the shape of the orbital is going to be where we have a 90% probability. See how it's darkest right here in the center? This is called an electron density map. This means that the electron is most probably, given that energy, most of the time, you have a 90% chance of finding it inside this area. That doesn't mean it has to be there. There's a probability it could be way out here. But most likely, the most probable place is going to be in here. Now again, Einstein, Schrodinger wanted things to be way more definitive than that. But the math says you never really quite know where everything's going to be. We just have the most probable place to find it. So they draw an orbital, and the 2p orbital is going to be this shape, based upon the probability in the math where that wave function squared tells us where the electron most probably is going to be found. So they say that if it's going to 2p, it's going to be in this area. Now, we go. Now, one other thing. Notice that there's a 2s. It can be a s orbital on the second energy level as well as on the first. Well, you know how they have the Russian dolls, and that one doll's inside the other one, they're identical in shape? Well, you got to put this one inside of this one. This is your 1s with the nucleus being a dot in the center. Then you have this bigger one surrounding it. 2s, a sphere. But there's a nodal region in between, an area of very low probability of finding the electrons in between. High probability here, in between, a nodal region, just like in that standing wave pattern when they cancel each other out, an area in between where there's a very low probability of finding the electrons. So then we go to n equals 3. What can L equal now?
0, 1, or 2.
0, 1, and 2. So L can equal 0, an S. L can equal 1, a P. and L can equal 2, which is going to be
D.
a D. Now the D's are way more complex. These are your D orbitals up here. Way more complex shaped. And we're going to talk about why there's 1, 3, 5 on the next one. And then lastly, n equals 4, what can L equal?
0, 1, 2, 3.
0, 1, 2, and 3. So L can equal 0, L can equal 1, L can equal 2, and L can equal 3. And 3 is going to be your
F.
F's. Now the F's are super complicated. Too complicated for me to have models of. But if you look at your F's, they look like this. Each one of these, even though they got all these lobes, that's one orbital. One orbital, one orbital. They're just very complex math. Where's the electron most probably going to be in these kind of complicated areas? And again, if you want to do, here's more electron density maps of d orbitals. So again, when they plug in the values, so n equals 3, L equals 2, plug in, they get these density maps. So you can see areas of high probability where you're going to find the electrons, but areas of low probability where you're not going to find an electron if it's got that much energy. The nodal regions. Okay? But if you remember, on the first energy level, it's only S. On the second energy level, it was S and P. On the third energy level, you have S, P, and D. On the fourth energy level, you have S, P, D, and F. Now, theoretically, when you go to n equals 5, you have a G. Now, backtrack. Why S, P, D, F?
Special defense.
Soldier, please don't fire. Okay, that was Graeber's little story. Okay, but the but the reality is that when we look at these bright line spectrums, we say, "Ooh, look at the pretty colors." But a spectroscopist, that's not just an upset scientist. Okay, a spectroscopist. With me. Everyone's gonna look at me like, huh? When they look at these colors, they can see 4 distinct different types of lines that are being given off. And they call them sharp, principal, diffuse, and fundamental. It's the type of lines that are given off that the spectroscopist can figure out, and so they named based upon where the electron, what orbitals the electrons are coming out of, they can tell the type of line that they're going to give. And so it's named sharp, principal, diffuse, and fundamental. Now, there's only really 4 different types of lines. But math says when you go to n equals 5, L can equal 0, 1, 2, 3, and 4. Well, 4 is a theoretical orbital, and they just go alphabetical after that, and they go G, H, and I. But the reality is, by the time an electron would have enough energy to be in a G, H, or an I orbital, it's so far from the nucleus that it's not going to be a help to the nucleus, and so it's escaped. It's like the West Wing in Beauty and the Beast, or was it the East Wing? Whichever one they weren't allowed to go into. West Wing was, I know, was a TV show about the president. Was Beauty and the Beast? Come on, Disney
It was
people.
West.
Was it West Wing? Okay. It was there in the castle, but it's forbidden. You couldn't go there. That's kind of where G, H, and I orbitals are. They're there theoretically in math. Hypothetically, they're there, but in the reality, electrons never occupy them because they would have to have so much energy they're going to be gone. All right. So we know then on the first energy level we can have s orbitals. On the second energy level we can have s and p. On the third energy level we can have sp and d. On the fourth energy level sp, d, and f. Fifth, sixth, seventh. You keep going. G, H, and I. Third quantum number is m sub L, which is known as the magnetic quantum number. And it can only equal minus L to plus L. And again, we always have to limit it. And this is having to do more with possible orientations in space. So if n equals 1 and L equals 0, well, M sub L can only equal minus 0 to plus 0. M sub L can only equal 0. That means there's only one possible answer for M sub L, which means there's only one possible orientation in space for an S orbital. Because an S orbital is spherical, there's only one way you can orient this in space. It's already 3D. There's no way to orient this in any other way. There's only one orientation possible for an S orbital. It's a sphere. But when L equals 1, M sub L can equal minus 1, 0, and plus 1. Minus L to plus L going through 0. Again, how many answers are there? 3. What does that mean? That means there's 3 possible orientations in space for the p orbital. It can be on the x-axis, it can be on the y-axis, or it can be on the z-axis, x, y, and z. Only 3 possible orientations. It's very axial. The p orbitals are very axial, so there's only 3 axes in space, x, y, and z. So there's only 3 orientations that a p orbital can be in. -1, 0, and plus 1. -1, 0, plus 1. Based upon what M sub L value you put into Schrodinger's equation, is it going to be on the x-axis, y-axis, or z-axis? When you go to L equals 2, the D, this is your P, this is now your D. What can M sub L equal?
-2, -1, 0, 1.
-2, -1, 0, 1, and 2. What does that tell me?
5.
5 different orbital orientations in space. Equal energies. All 5 of these are what we call degenerate orbitals. Degenerate means equal energy. 1, 2, 3, 4, 5. 5 different ways that things can orient themselves in space. And then finally, when L equals 3, is the F. What's M sub L going to be? I heard somebody say -3, -2, -1, 0, 1, 2, and 3. How many answers is that?
7.
So how many orbitals are there possible on the F sub level?
7.
7. Okay? That's why we have what we have in our 1s2, 2s2, 2p6, all the way up. It's because of these quantum numbers from Schrodinger's equations, which describe why an atom can give off the colors that it gives off. And lastly, the last quantum number is M sub s. Is the spin quantum number. Okay? And that's just going to be plus 1/2 or minus 1/2. And this is from the Pauli exclusion principle. Anyone remember what the Pauli exclusion principle says?
It like depends on the amount of electrons it has, and like it like.
Okay, you're really warm. How many electrons max can be in an orbital? No, that's in a sublevel. Or well, actually, that's the filled octet thing. How many in any given orbital? How many electrons can be in here?
2.
2. And what must be true about them?
They can't go in the same way.
They have to have opposite spins, which is kind of like their charge. The plus 1/2, minus 1/2. Now again, the value of plus 1/2, minus 1/2 it's just they have to have opposite spins. Now, most of my teaching career, I always kind of taught, got a clockwise spin, you got a counterclockwise spin. As they spin, they generate a magnetic field. That magnetic field has to be opposite for 2 negative things to occupy the same space. All right, and that's really easy for my brain to wrap around. But I did read something about 3 or 4 years ago that said that the electron's really not spinning like the Earth is spinning on its axis. That the spin is more like just kind of a random kind of charge type thing that's not like a normal charge. It's just, quantum mechanics doesn't follow anything, but just think of it like it's actually spinning and it makes a whole lot more sense. But I just want to cover my bases here. It's really not spinning. It's high level math that differentiates. But they have these opposite spins. They call it the spin, so they can occupy the same. So only 2 electrons in any one orbital, and they must have opposite spins. Okay? So all of our electron cloud is based upon these quantum numbers that on the first energy level you can only have an S. On the second energy level you can only have an S and a P. And on the third energy level, so when we're looking at this, here's the nucleus. On the first energy level you have an S orbital. On the second energy level you have a bigger S orbital. But then you also can have your P orbitals. So it's gonna, if you look at it from the outside, it's gonna look like one big sphere of electrons. But the reality is it's very subdivided on the inside on where the electrons can be based upon the energy, and Schrodinger's equations kind of describe that. If we go to the third energy level, we have a bigger sphere. A nodal region in between where there's a low probability of finding electrons. But then we have bigger, I don't think this is going to write very well, but we'll see. We can now have our d orbitals, our p orbitals, they're just bigger. Same shape. So the electrons are now out here. These electrons are pretty much kind of hanging out here, and you have this nodal region in between where there is a low probability of finding an electron. And then we go here. Now on top of this, we would have to superimpose our 5 d orbitals. You have to put these shapes in there. I'm not good enough an artist to be able to draw those in there.
How'd they figure all this out?
Schrodinger, a very smart guy. Now, to be honest, history says that Schrodinger was quite the ladies' man. Okay? And he had a lot of mistresses. And apparently he was on a romantic liaison in the mountains at a resort to where he got inspiration, and during that romantic liaison he had moments of brilliance, and he came up with this whole idea of his quantum numbers and did all the math, figured it all out while in the mountains having a romantic liaison with one of his mistresses. Now, I do not recommend that as a study technique or as a motivation for academic genius. But apparently that is what worked for him. So I recommend studying and learning your math. So they're just very smart. I don't know, those guys back in the 20s, 1900 to 1930, they were just geniuses. And even in the Oppenheimer, to figuring out how to split the atom and all that, because I think they had to really work at everything, they didn't have everything at their hands in a phone. I think we just get lazy in our brain because everything's at, hey Siri. And so they had to ponder and think and work through stuff, and they did. So this is our complex math. Now, y'all have all this down? It's too pretty to erase, but I have to. Can I just show the video in the next class? So our model now, this is what we did. We did our arrow diagrams, our orbital notation last year. We have on the first energy level, you have just the S, and you only have one S orbital. That's your sphere. On the second energy level, you have your S, and then you have your 3 p orbitals. Now the p orbitals are slightly more energetic than the S, which means that they're not held as tightly to the nucleus as the S's are. And we'll talk about that probably tomorrow. Time keeps on slipping. So on the third energy level, what do we have? What orbitals? S. The P's. You have 3 of them, but now it's going to be 3p. And then what other sublevel is possible?
D.
The D's. And how many are there?
3.
How many orbitals on the D sublevel?
5.
5. 1, 2, 3, 4, 5. And the D's are slightly more energetic. When we say more energetic, that means not held quite as tightly to the nucleus. The lower energy they are, the more tightly it is held to the nucleus. All right. So if I'm going to stop right there, now I want to know how the electrons of, say, arsenic, element number 33, how are the electrons of arsenic arranged? Well, I got 33 electrons. I'm always going to start in the ground state, the lowest possible energy state. Electrons always want to be in the lowest possible energy state. So we're going to go, how many electrons can go in any orbital?
2.
2. So we're going to go 1, 2. So if I'm saying arsenic, element number 33. Then we go here to the 2s, 3, 4, and we fill up the 2s before the 2p because it's lower energy, and everything in nature fills the lowest energy first. Okay? So then, when we do the 2p, who remembers, how do we fill that p sublevel?
You go one by one.
1 into each, and then you begin pairing up, because electrons are still negative. They're not going to go into the same space if they don't have to, because they're going to repel. Now, Hund's rule says that they have to have the same spin. They don't have to all be up. They don't have to go up first. They can all go down first, but they have to be the same. So if you want to be more of a downer, you could be down, 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 and then go up, up, up. Or you can go up, 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 down, down, down. You also don't have to do it in terms of typewriter. You don't have to go left to right, because all 3 orbitals are equal energy. They're degenerate. So the electrons can fill them in any order. They're all equal energy. So we can go 1, 2, 3, 4, 5, 6. Now, I tend to do typewriter, 1, 2, 3, 4, 5, 6, just to kind of keep it going. Okay, now that's 10 electrons. So that would actually be what the electron configuration is for neon. And if you ever want to stop and take a gaze, here's a kind of a diagram of what that would look like for neon with your s orbital, 2 electrons down here in the 1s. Then you got your bigger 2s here. Then you got your p orbitals here in and out in the z orbital for a total of 10, all kind of superimposed on top of one another. Okay? You might want to look at this on your way in or your way out next time. Just kind of get an idea of what the nucleus is going to look like. As we continue on, go to 33, that's 10, 11, 12. I'm not going to make it. I didn't go do it right. That's 2, 4, 10, 12, 13, 14, 15, 16, 17, 18. We'll stop there because I don't want to explain why the next one is where it is.